Okay, these are the video notes for Chapter 7, Section 1. I do want you to print out these notes and put comments on them and hand them in to me on Tuesday. Alright, this section brings together previous ideas in an important way. We talked about series and sequences. Remember what a series or sequence is. We'll start with sequence. It's a set of numbers that get closer and closer to a particular number. Series are derived from that. Series and sequence actually are somewhat interchangeable. You can create a series from a sequence and vice versa. In this chapter, we'll be talking more about series than about sequences. Now, in particular, we've talked about Taylor series also, where you don't just approximate single numbers, but you approximate entire functional values. Right? If you take the series approximation of e to the x, then you'll get a Taylor series. And if you plug in different values of x, then you can find what e to the x is using the same series. So we're kind of going to build off of that kind of idea of approximating entire functions, not just single function values. All right, so that's one strand that we're bringing into this new section. Another strand is successive approximation of whole function properties. When we did Riemann integration, we created these dissections and found u of f and d and l of f and d, and we could find dissections so that these u and l were arbitrarily close to the Riemann integral of the function f. So here we are also having an approximation technique. This time we're not just looking for function values, we're looking for what I'm calling whole function properties, properties of that depends on the entire function, in this case the integral. In this section, we'll introduce sequences of functions, not just sequences of numbers, but sequences of functions. It's kind of like Taylor series, but we're doing it with a twist. We're looking for sequences of functions, so I'm calling them f1, f2, fn, and so on. Think of these all as functions of x, and it would all be defined on a common domain AB. Okay. But we want to approximate the function f of x arbitrarily closely so that the whole function properties are also approximated by the sequence. In particular, the integral is one property that we're going to be looking at. Another property is continuity. We want to approximate a function in such a way that the continuity properties carry over from the functions in the sequence to the limiting function. If we can do this successfully, then for all practical purposes, we can replace the function f of x, the limit function, with one of the functions fn where n is large. And this is what you actually do in practical applications. When you compute functions with a computer, for instance cosine or sine or some other function, you don't have that exact function. What you have is essentially a sequence of functions that can be made arbitrarily close to that function. And you need to make sure that the function that you actually use, the approximating function, is close enough to the actual function. Another very important application is Fourier series that you might have heard of, that you approximate an arbitrary function as a series of sines and cosines. Okay. This approximating of functions by other functions is not quite so easy as it sounds. It's possible to make successive approximations that have very bad properties. So let me give an example. I'll draw a set of axes here. There's my straight line, so to speak. And the idea of my functions is that I'm going to do, and we've seen this kind of before, I'm going to take a series of functions that moves closer and closer into 0, gets higher and higher, and narrower. And so this is going to be my f1. f1 is going to be 0 except on this interval, so this is f1. f2 is going to be higher. In fact, the way I define it is going to be twice as high. Here's f2. It's going to be twice as high and half as wide. f3 is going to be twice as high as that and half as wide again, and so on. So I'll just define this sequence of functions. So how would I actually define this? Well, because we're going to be defining it for an arbitrary n, I'm going to say fn, fn of x, okay, it's the function value is either going to be 0 or it's going to be 2, I'm going to call it 2 to the n. Okay, so that reflects the fact that as n gets larger, the value of the height of the function gets higher. So I really should do this otherwise. This 0 is going to be otherwise. And 2, I'm going to have it be 2 to the n on a particular interval. All right, well, for n equals 1, I want it to be 1 on the interval from 1/2 to 1. Okay, so I think my lower limit here is going to be 2 to the minus n. And that's going to be between 2 to the minus n and x and 2 to the minus n plus 1. Let me rewrite that. That upper limit there is 2 to the minus n plus 1. Okay, so that works in this case. When n equals 1, the function height is going to be equal to 2 on the interval from 1/2 to 1. Let's look at n equals 2. For n equals 2, I'd have the function value is going to be 4 on what interval? 1/4 less than x less than 1/2. Now I should be a little bit careful about the less thans here. I suppose I'll make this be less than or equal to up here. Okay. All right, and this function and all of these fn's are defined on the interval 0, 1. So they all go from 0, 1 to r. Okay, my picture here is not to scale, but you get the idea. The functions are going, the successive functions are getting higher and higher. The base is getting narrower and narrower, and they're getting closer and closer into 0. And this here is the formal definition. Now, what I would like you to do when you hand in these notes is I'd also like you to go ahead and show these two things. I want to show you that the functions, as I've defined above, as it turns out that the fn of x will be equal to 0 when n is sufficiently large. In particular, when n is bigger than log 2 of x plus 1. What does that mean? The larger n is, what's basically happening is that as n increases for any fixed value of x, and let me draw a picture. For any fixed value of x, what's going to happen is that whoops, that's not what for any fixed value of x, let me draw my axes again here. It may be that the function starts out here, and it goes up, and it goes up. It's going to hit that one, for only one of the fn's is fn of x going to be equal to 0. Then as n increases, basically the peak of the function sweeps past and passes by the x, gets closer and closer to 0. So that's kind of how it's working. So that's why this is true, why fn of x is 0 when n is bigger than log 2x plus 1. So see if you can prove that. The other is, this should be pretty easy directly from the definition of fn, is that the integral of fn of x is equal to 1 for all n. So what does that mean? That means that no matter what x I have individually, fn of x is going to converge to 0. However, overall, the integral of fn of x does not converge to the integral of 0, even though we call this pointwise. Even though pointwise fn of x converges to 0, overall fn of x, the integral of fn of x, does not converge to 0. So this is an example of a pathology that can happen if you're not careful about how you make the functions fn converge to the function f. Okay, so in order to keep bad things from happening, like we saw in the slide that we just covered, the example we just covered, we're going to have to be careful about the notion of convergence of functions. We'll have to define a special notion of convergence. This convergence has to be even across the whole function and not lumpy. In the example I just showed, there was a lump, you could call it a lump, in the functions fn, that as n increased, that lump traveled to the left and towards 0. And since that lump was always moving, it didn't permanently affect any of the x in the domain. However, it caused a error bad enough so that the overall integral of the functions fn did not converge to the integral of the limiting function. All right. This idea of even convergence may recall to mind the discussion of uniform continuity that we gave in section 3.6. In that case, for any epsilon greater than 0, we found a delta greater than 0 that worked for all x in the domain. That is, we had a uniform wiggle tolerance. All right, so let me explain what I mean by that. So let me draw my axes and my function. So let's say the function looks something like this. Okay. All right. Now, the whole idea about uniform continuity is given any epsilon greater than 0. So epsilon is going to be my vertical wiggle. So here we have plus or minus epsilon. I was off the edge of the screen there. There's plus or minus epsilon is represented by this up and down arrow. So we should be able to draw an envelope around this function, plus or minus epsilon. There's the plus epsilon, there's the minus epsilon. Okay. So if I label this one here is f, this one here is f plus epsilon, and this one here is f minus epsilon. Now, uniform continuity meant that there was a left-right wiggle, delta, and I'll use a different color for that. All right, there was a left-right wiggle, delta, that I'll indicate this way, such that I could move this function to the left or right by delta, and it would still remain within this sleeve that I've created here. So here's the left function. That's f minus delta, and then this would be, this would be f of x plus delta, and here would be f of x minus delta. Okay. So this one here is going to be f of x. Let me see if I got it right. This is going to be, because this is over here, this is going to be f of x minus delta. And then this one here is f of x plus delta. Okay. But the whole idea is that we had this uniform sleeve such that for if we made our left-right wiggle small enough, we could keep the function uniformly within this sleeve. Okay, so that was a left-right wiggle. Now we're going to allow for an up-down wiggle. So let's see how that works. Okay, so I'm going to draw my function again. And let's do a up-down wiggle. So I'm going to draw this sleeve just like I did last time. Okay, so this here is f, and here is f minus epsilon, and here's f plus epsilon. And the whole idea is if my function g is uniformly close to f, it should be within this sleeve everywhere on the domain. Now we're treating functions from a to b. All of our functions are on a specific domain, even if I don't mention it. So here's our domain. So the function g must lie within this sleeve in order for g to be uniformly close to f. So let me show that. So my g would have to be somewhere, would have to remain in this sleeve. So basically everywhere my g is close to my f. Now clearly, the previous example I gave with a traveling bump, that was not going to be the case because the difference between that bump function and 0 was getting larger and larger as n went to infinity. Okay. All right, now look at this picture. In order for two functions f of x and g of x on AB to be within epsilon in this sense, what's the worst possible difference you can have between the absolute value of f of x minus g of x? What's the worst possible case? Well, since it can't be outside this sleeve, and here's the worst case right here, since it can't be outside the sleeve, the biggest, for any fixed x, the biggest difference that you can possibly have between the two functions is epsilon. Okay, So that is, if we use this notion to define closeness of f to g, then we say that f of x is, quote, within epsilon of g if since this is the maximum over the whole interval, if the supremum of x element of AB, so the worst possible case of f of x minus g of x, even the worst possible case must be less than epsilon. Okay. So here's a notion of closeness between functions that is basically uniform. It applies uniformly across the entire domain. So let's formalize this concept of closeness. We're going to make it depend on a notion of distance between two functions. Now, you're used to distance between 2 points in 2 dimensions or 3 dimensions. We can generalize this notion of distance. The general mathematical term for a generalized distance is called a norm. And a mathematical norm should have the properties that we typically associate with the distance between points in space. This particular norm that we're going to be defining, Howie just calls it the norm. It's also called the infinity norm, or it's called the sup norm. There are other norms that you use with functions. That study is called Banach spaces. We won't be getting into that. Okay, the actual definition of the sup norm is given in equation 7.1, and that's on page 181. And you can see that it depends on the supremum of the function value. So it's very close to the notion of distance between two functions that I gave previously. Now, theorem 7.1, also on page 181, so both of these are on page 181, it shows that this sup norm satisfies 3 key properties that we'd expect of a measure of length. Okay, what do you expect a measure of length or distance to be? What do you expect to be true? Well, if a length always should be positive. So this is positivity. And the only time that the length is 0 is if the vector itself is 0. We're really talking about lengths of vectors. In fact, functions can be considered as vectors in this application. Another important property of norm is the triangle inequality. Okay, and you can see that on page 181. Typical form of triangle inequality, right? You just take the two sides. The length of the hypotenuse is less than the sum of the lengths of the sides. Or for any triangle, don't need a hypotenuse, can take any triangle, and that's true. Okay. Then the last one is scaling. If you scale your vector by a constant value, then the length should also scale by the same amount. So you should write these down on your notes. These are the 3 key properties of length that the norm satisfies. Okay, theorem 7.2 is closely related to theorem 7.1. It shows that the length notion that we've defined by this norm, the sup norm, gives rise to a distance, the distance we want with common distance properties. Distance you also expect to be positive, unless the 2 points are concurrent, the 2 vectors are concurrent. The second one, we have symmetry. Okay, you expect the distance not to depend on which vector you take first. The third one is also triangle inequality. Okay, so these also are the properties of distance between 2 vectors that we would expect. Now, we've defined convergence before. It turns out that whenever you have a measure of distance, you can always use that to define a notion of convergence. If you think back about our definition of convergence, there was really nothing special about absolute value. We could put any distance in there. So the sequence fn converges to f if and only if for all epsilon greater than 0, there exists n greater than 0, such that here we're using the 2 lines to denote the norm. Fn minus f Remember, when we first defined convergence, we just used absolute value, but we're just plugging this in. Same thing works. Is less than epsilon. And here I should put an m here. For all m greater than n. Okay, general notion of convergence. Okay. This particular notion of convergence, when we're using convergence relative to the infinity norm or sup norm, this is called uniform convergence. All right. If you look in Howey's book on page 183, you'll show that uniform convergence is quite a stringent condition in the sense that it implies other things. Remark 7.3 says, if functions converge uniformly on an interval AB, then they'll also converge uniformly on any subinterval, which is a handy property. You don't need to worry about establishing it again for subintervals. Handy property. Okay, theorem 7.4 says if if functions converge uniformly on an interval, they also converge pointwise. Pointwise is our usual convergence using absolute value for each individual value of x. So I can say this for each individual x element of AB. Okay. Uniform convergence is a stronger condition than pointwise convergence. Very important. Okay. The example on page 184 shows a sequence of functions where it converges pointwise but not uniformly. And in fact, the example I gave at the beginning of this lecture is another example of such a case. All right. Now, this strong condition of uniform convergence gives us preservation of whole function properties, which is very useful. Like I said, this means that if we have a uniformly convergent sequence, then if we take one of the fn's for large n, that we're essentially have the same function as the limiting function at the end. Okay, so theorem 7.5 says the limit of a uniformly convergent sequence of continuous functions will also be continuous. In other words, what I could call the whole function property of continuity is preserved under uniform convergence. I don't need to worry about my limiting function going crazy as long as the functions in my sequence are continuous. Okay. Another important property of uniform convergence, the limit of a uniformly convergent sequence of integrable functions is integrable. Okay, so integrability is preserved by uniform continuity. And the integral of the limit, I could say the limiting function, is equal to the limit of the integrals. The way you'd write that is the integral of the limit of fn is equal to the limit, is equal to, let's cross that out, put that down here. The limit of the integral of fn is equal to the integral of the limit of fn. You can exchange limit and integration only if you have uniformly convergent sequence. Theorem 7.7, similar to 7.6, the indefinite integrals of a uniformly convergent sequence of integrable functions converge to the indefinite integral of the limit. Okay. All right, so I could say 7.6 is like this. The limit of this definite integral works, and 7.7 says this, that the limit of, as n goes to infinity, of integral from a to x of fn of x, of fn, let's call it y, dy, is equal to the integral from a to x of the limit as n goes to infinity of f of y, of fn of x, fn of y, dy. Okay, and that's it. Make sure that you have all this information on your notes and hand it on Tuesday.